Today, we're going to go over data representation, binary and hexadecimal. Okay. This is something I didn't learn in school. I had to learn this outside of school. So I thought it was important that I teach you all this since you all are going to be, super programmers in the future, making hundreds of thousands of dollars. So I think it's important that you at least understand what binary is and how to convert from binary to hexadecimal to decimal. All right. And what they are. All right. So binary is base 2 numeral system. So there's only two possibilities in binary, either a 0 or a 1. Either the light bulb is off or it's on. All right. And so when I talked about the processors last time, and I talked about transistors are little, if I can equate it to anything, little tiny light bulbs. Either they're off on their own, I'm sorry. Depending on their value, your computer is capable of doing so many different things. The fact that we are able to talk through a video chat right now over the internet in real time all breaks down to zeros and ones. Network communication is sent bit by bit, meaning either a 1 or a 0 is sent based on electrical impulses, right? So anybody who's interested in electrical engineering, that's the foundation of computing, is electrical impulses and how they are sent across a network, across physical copper wires. One thing that a lot of people don't realize is that over the internet, most of the internet is physical wires. It is not wireless. Although we have gotten accustomed to wireless communications, cell phones, and Wi-Fi, most of the internet is still physical wires. For example, if you want to connect to a website, an international website that has its servers in the UK, your data is traversing wires that are transatlantic. They all go all the way across the Atlantic to the UK and back. And it does it like that, right? And we expect it to do it, in near instantaneously. And that's just, the magic, if you will, or the incredible capabilities of technology today. But again, it all breaks down to zeros and ones. And then the computers interpret those zeros and ones, those electrical impulses, into machine readable code. So what is a bit versus a byte? Can anybody tell me what a bit versus a byte is? What's the difference?
Isn't the bit I know a byte is 4, right?
A byte is
Or is it
8.
2?
8
Oh, okay.
8 bits. That's the only difference. A byte is 8 bits. And the reason being is most computers in memory are stored in bytes. Okay. So when we talk about, hold on just a second. I'm trying to do a couple of things at the same time. So when we talk about storage, we always talk about megabytes. We talk about RAM, we talk about gigabytes. We talk about, again, storage, terabytes. But when we talk about network communications, it's always megabits per second, right? Gigabits per second. The reason being is in memory, it's stored on a per byte basis. So you have 1 byte, 2 byte, 3 byte. Whereas when it comes to network communication, everything is sent bit by bit. So talking in terms of bytes makes no logical sense. So you would just say 1,000 megabits, or that's 1 gig, by the way. So again, when we talk about bytes, 1 kilobyte is 1,024 bytes. 1 megabyte is 1,024 kilobytes. 1 gigabyte, 1,024 megabytes. And it's all based on 2 to the power of something. Again, binary is base 2, so it's always 2 to the power of, right? 2 to the power of 0 is one byte. 2 to the power of 10 We got a kilobyte, 2 to the power 20, megabyte. When we talk about gigabits, again, it's 1,000 bits for a kilobit, 1,000 bits, 1,000 kilobits for a megabit, so on and so forth. Just understand that 1 kilobyte is 1,024 bytes, 1 megabyte is 1,024 kilobytes, and so on and so forth. And we'll talk about how to convert from bytes into decimal. So if I have 8 bits, what is the value in decimal? We'll talk about all that as we go through this. So I kind of just talked about this. Again, in memory and storage, we always talk about megabytes. 32-bit system has 2 to the 32 unique memory addresses. That's what makes it a 32-bit system, which is roughly 4 million addresses, meaning there are 4 million placements in memory that you can store data. Versus a 64-bit system, and you might think, okay, 32 to 64, we just doubled the number. No, we're talking about 2 to the power of. So each time we're doubling that number. So we went from 4 million unique addresses to 18 quintillion. All right, and that's the full number written out. So computers nowadays can hold far more data than they were previously. Most computers previously were 32 bits. We switched over to 64 bits, and you see we increased the number exponentially. So if you haven't gotten anything from what I've talked about so far, is that the things that we use every day, so simple, are incredible little machines. All right. A funny statistic or a funny fact I heard, those little birthday, cards, you open it up and they start playing music, have more processing capability than the first rocket to the moon, the rocket that put man on the moon. So we use these cell phones every day. These cell phones are more powerful than the first rocket to the moon. And we just use them every day. We toss them out. They start getting slow and useless, yada, yada, yada. However, they are incredible machines. And everyone, it seems like I have to remind you all every class, if I don't see your face, you will get booted from class, all right? If you don't want to be here, I'm not forcing you to be here. All right, so how do we convert from binary to decimal? So if I give you this number, 00101011, how can we convert that to decimal? It's actually pretty simple once you learn the tricks. So I spread it out, right? 00101011. Okay. All you have to do is multiply by its position. We always start right to left. So on the right side, the most significant bit, because depending on what this number is, if it's a 0, your resulting number will be even. If this number is a 1, your resulting number will be 1. Okay. Oh, I'm sorry, odd. And this will become clearer as we go through this. So again, what you do is multiply it by its position, and then you add it all up. So 2 to the power of 0, it's the 0 position. Again, in programming and in computing, we always start at 0. 2 to the power of 0 is 1. And anything to the power of 0 is 1. Times 1 equals 1. 2 to the power of 1 equals 2. Times 1, again, equals 2. 2 squared equals 4. Times 0 equals 0. 2 cubed equals 8. Times 1 equals 8. 2 to the power of 4 equals 16. Times 0 is 0. 2 to the power of 5 is 32. Times 1 is 32. 2 to the power of 6, 64, 0. 128, 0, 0. So basically, if there is a 1, we bring it down. If it's a 0, We don't. Once you've brought all of your numbers down, you add them up, and that's your final total, 43. Let's do another example. So before I even do this example, will this number be even or odd?
Even.
Even, correct. Because our most significant bit is a 0. All right. So we break this out. 110101110. Again, if it's a 1, we bring it down. So from looking at this, we're going to bring down 128, 64, 16, 4, and 2. We bring those down and add them all up, and this is our total. Any questions about that? All right, try to do the first 2 of these. And now, granted, I know there are calculators. I'm not a fool. But I encourage you to actually try. What's the harm in learning how to do this conversion on your own without a calculator? All right, so I'm going to give you 10 minutes. Actually, I'll give you to 11:20, and then we'll review this. All right. If you have any questions, let me know. All right, so let's go over this. Okay, so this was the first number, 100101101. Okay. And again, if it's a 1, we bring it down. If it's a 0, we don't worry about it. We always start right to left. So on the right side, we have 2 to the power of 0, right? Which is actually a 1. So we bring that down. Again, this would be 2 to the power 1, but we know that's a 0, so we're not going to worry about that. This is 2 squared, which is 4. We bring 4 down. Next one we don't worry about. This is 2 to the power 4, which is 16. Bring that down. This would be 32. We don't worry about. 64. We don't worry about. 2 to the power 7, which is 128. All right. We add these up, and our total is 444, 48, 149. Did everybody get that?
Yes.
Yes, sir.
All right. So let's do that second one then. And again, if you have any questions, stop me so I can help you. So we know we have these zeros, so we don't worry about these. 1, 2, 3. This would be 2 to the power of 4, which is 16. We don't have that one. And as you get better than this, again, I'm saying 2 to the power of 4 so that you know that it's based on positioning. But as we get better at this, you don't have to really worry about 2 to the power of 4. You can just put 16 if you like. If you are that good, if you understand where it comes from, you can just put 64, 128. 128, 64. Add those up. 80 plus 128, 208. Did everybody get that? Yay, nay? Good.
Yes, sir.
All right. Cool. All right, so let's do the opposite way. Okay. How do we go from decimal to binary? Okay. So let's give you, and one thing I didn't tell you, all of these numbers, if you have a byte, 8 bits, the maximum number is 255. The minimum number is 0, right? So it's always going to be within that range, 0 to 255. Okay. So if I give you this number, 237, how would we go from 237 down to binary? Okay. So when we're doing binary, from binary to decimal, we start right to left. In this instance, we're going to start left to right. So we have 237. Okay. The first position, of course, is 2 to the 7, right? 2 to the 7, which is 128. Is our number greater than or equal to 128?
No,
Is this number up here greater than or
I
equal to?
meant yeah. I meant yeah. I meant yeah.
Lord have mercy. We don't know geometry, nor do we know greater than or equal to. Yes, it is. So we got a 1. All right. We subtract 128, which is, looks like it is 109. 109, right? After we subtract 128. Our next number is 2 to the power 6, which is 64. Is our new number greater than or equal to 64?
It's greater than.
We bring down a 1. Subtract 64. And that new number is, ooh, Lord have mercy. The 36 plus 9, 45. And if my math is wrong, please correct me. So the next number is 2 to the power of 5, which is 32. Is 45 greater than or equal to 32? Yes. We go down to 1. Subtract 32. That is 13. Is 13 greater than or equal 2 to the 4, which is 16? No. 0. And we just pull 13 over. Greater than or equal to 2 to the 3, 8. Yes. It's always funny, you know, when you're writing on a whiteboard, you start off so big and then you get towards the end and you start having to write really small. So I'm going to just drag this over a little bit. All right. Subtract 8. We got 5. Is 5 greater than or equal to 2 to the power 2, which is 4? Yes. Pull down the 1. Subtract the 4. We have 1. Greater than or equal to 2 to the power of 1, which is 2. That's a no. Pull over the 1. Greater than or equal to 2 to the power of 0, which is a 1. Yes. So our final number is 111,011,01. All right. We start left to right. Did everybody follow that? All right. Let's do another example. Let's do 96. All right. So 96. Is it greater than or equal to, and again, if we're good at this, 128? No.
Nope.
Yep. So we pull 96 over. Greater than or equal to 64? That's a yes.
Yep.
Yep. Pull 1 down. Subtract 64. I believe that's 32. Greater than or equal to 32? Yes. Subtract 32. Well, we know we have 0. At this point, we're done. The rest of these have to be 0. We're done. 0, 1, 1, 0, 0, 0, 0. 0. One more 0. And that's our number. All right. Does that make sense? Because now it's your turn.
Yeah, because since you subtracted 32, you can't use no more.
Exactly. Exactly. All All right, so now I'm going to turn it over to you all. So convert 89 and 112 to decimal. And again, I'll give you about 10 more minutes. So 10, actually 11:35. I'll pick back up. So we are converting 89 and 112, right? Those were the two numbers. 89 and 112. Again, we always start left to right. So let's do 89. Is 89 greater than or equal to 128? That's a no,
No.
right? Yeah. So 0. Pull 89 over. Greater than or equal to 64? Yep.
Yep.
Yep. So bring down a 1, subtract 64. That is a 25, I believe. Greater than or equal to
25.
32? Yep. No. Pull 25 over. Greater than or equal to 16? Yep. 9. Greater than or equal to 8? Yep. 1. 4? Nope. 2? Nope. Yep. And there's our number. Did everybody get that number? All right.
Yes.
So 112. Why don't you go up? 112. Greater than or equal to 128? Nope. Greater than or equal to 64? That is a, what is that? 48? Is that 48? Afterwards, 112 minus
Yeah.
64? 48. All right, cool. 32. That's 16. Yep. And then we have a 0. So at that point, everything else is going to be 0. Did everybody get that number?
Yep.
Cool.
Yeah.
All right. Now you know hexadecimal. All right. So go off and be great. That's all you need to learn. We got a lot more to do. So this, again, this week and I think a little bit into next week, we're still doing kind of intro to computers. However, once we get into programming is when we really hit, what this class is about. But I do think it's important that you all understand the foundations of computing. All right, so hexadecimal is a little bit different because in computing, we can have very large numbers. So for example, if you think about Bitcoin, is everybody familiar with Bitcoin? Cryptocurrencies. All right.
Yeah.
If you've ever seen a crypto address, it's a very long string of numbers and letters, typically written in hexadecimal. Okay. Reason being is a Bitcoin address is actually 256 bits. All right. 256 bits. So if you think about it, 256 zeros and ones. Human readability, I'm not going to understand 256 zeros and ones. All right. So what they did is, instead of just doing that, you take 16 at a time, convert that to a letter or a number. And if you look here, 0, 0, 0, 0, so 4, I'm sorry, you take them 4 at a time, not 16, 4 at a time. So 0, 0, 0, 0 in binary is just all 4 zeros. In decimal, that's a 0, right? We convert that to decimal. In hexadecimal, it's a 0 as well. All ones is a 15 in decimal and an F in hexadecimal. And so everything in between falls within those two ranges, a 0 or F. So we take them at 4 bits at a time. And that reduces 256 divided by 4. So instead of 256 individual numbers, now we're looking at just 64. Little bit more human readable, although not by much. All right. So here's the table. Hexadecimal, I just give you the table. All right. There's only a certain number of values possible. There are 16 values in hexadecimal, ranging from 0 to F. And here's what you get right here. So in binary, 4 zeros is a 0 in hex. 4 ones is an F. Right? In hex, if I have an A, that's 1010 in binary, or a 10 in decimal. Okay. So again, this was just this was just to reduce the number of numbers that we see on a screen, right? From human readability standpoint. So we have this number in binary and we want to convert it to hexadecimal. Okay. So again, I give you the table, which makes it a lot easier. All right. So we break it down, 4 bits, increments. We convert it to decimal if we want to, but we have the table, so we can do the direct conversion. And then from decimal, it makes it really easy. All right. Same thing here. We break it down into the 4-bit increments. We can convert it to decimal if we want. However, we have that table, so it makes it really easy.
Quick question, Professor Brown. Are you saying we have the table come to test time, or what do you mean by we have the table?
So the table in general, we have it at our disposal, but lucky for you all, this won't be on the test. So that doesn't mean you shouldn't be paying attention, though, right? I still want you all to pay attention. However, this will not be on the test. Right? This is more so, again, setting the foundation of computing, because as you all get better and better, because I expect you all to be super programmers in the future and making, hundreds of thousands of dollars and far outshining me, you will come across hexadecimal, maybe binary, but I'm pretty sure you'll come across hexadecimal at some point in your programming careers. All right, so if we go the opposite way, hex to binary, again, we split it out, and we know each one of these is 4 bits. So we can convert it to decimal. We can do that intermediary step if we like. However, we can go straight to binary as well. All right. So I will talk about networking next time, because we only have 10 minutes and it's actually pretty interesting. So I'll talk about that next time. Also, I'll talk about operating systems as well. So what's the difference between Windows, Mac OS, and Linux? Once we do that, I believe we have the lab on Friday. Starting Monday, I think we're still online. But on Wednesday, we should be in the classroom. All right, next Wednesday, February 2nd, I believe. Don't quote me on that. Obviously, look out for university communications. But I believe we're getting close to being back in the classroom.